Today we're going to relate the number of electron domains in the valence shell of an atom to the geometrical arrangement around that atom. So big deal, molecule shapes. Explain why non-bonding electron domains exert a greater repulsive interaction on other domains than bonding domains do. That's basically the crux of the valence shell electron pair repulsion theory. The quest that goes with this is structures Vesper. All right, so looking at this breakdown again, we've seen a chart very similar to this. When we're talking about molecule shape, we're specifically talking about things that covalently bond. When we start looking at the molecule shape, it will help us inform whether or not a molecule will be polar or nonpolar. It will also help us figure out what kind of interactions it will have with other molecules, including our intermolecular forces, hydrogen bonding, dipole-dipole, and London dispersion. If you haven't heard of those things before, or if you heard about those things in honors, don't worry, we will review them again, coming up in a later unit. So, with the Lewis dot structures, the great thing about Lewis structures is that we can use them to figure out the formal charges of molecules, and we also can use them to accurately display resonance. That's what we've done so far. So we've successfully done formal charges, we've successfully looked at resonance. Now we're going to look at how things are arranged in 3D space using the Vesper model. I know it's spelled V-S-E-P-R, Vesper. If you call it Vesper, no one's going to know the difference. It just rolls off the tongue a little bit easier. That's why we refer to it as Vesper. So with this, we'll be able to look at the molecule geometry. We're talking geometry, we're talking about the shape, bond angles between two atoms, and its attachment to the central atom. We've talked about bond energy a little bit already, so using this model helps us figure out which bonds we need to break and or form when making new molecules and reactions. Bond length, that's going to be related to single, double, and triple bonds, as we saw previously, and when we talked about bond order. And it's also going to help us with polarity. We know that there are polar and nonpolar bonds, and that uneven distribution of electrons will contribute to the overall polarity of a molecule. All right. Okay, so we have the valence shell electron pair repulsion theory. Vesper for short. So if we break down what that means, we have electron groups, also referred to as domains, that can be used to predict the 3D shape of our molecule. It's based on the idea that domains will repel each other due to the negative charges of the electrons and the electron clouds. Since these electron groups will repel each other, they will attempt to move as far away from each other as possible. Obviously, everything that's attached to the central atom only has a certain amount of space to move, and so we're going to really look at how those things move in 3D shapes. Okay. So there's a great molecule shape simulation from PhET that shows all of these things. I highly recommend checking it out. They have some real molecules here, and then they have the models. And so when you come here, make sure you have the molecule geometry and electron geometry checked, and even bond angles. I like showing the bond angle. So bond angle is going to be really important when we start building molecules. We're going to be doing a bonding lab at some point where we build some molecules, and we'll see the different arrangements. So here's one that has two bonding groups. It has two atoms attached to the central atom, and there are no lone pairs on the central atom. When we have only two things attached to our central atom, they want to move as far away from each other as possible. The furthest possible distance they can move away is 180 degrees from each other. And you'll notice that if I try and grab one of the atoms and try and move it closer, I temporarily decrease my angle, but they naturally push away from each other, which is really cool. And the minute I let it goes back to 180, because that's the furthest possible distance. So this molecule geometry is referred to as linear. I'll talk about the difference between molecule and electron geometry shortly. If we were to add another bond, we now have 360 possible degrees to work with in a circle, and so we divide that by 3 and we get our 120 degrees. Now this molecule actually is rather flat. If you're looking at it on a plane, it's on the same x and y axis if we're looking at it that way. If I try to move these close to each other, they temporarily get closer, but then when you let them go, they all reestablish back to 120. By doing that, we end up getting 3 bonding groups, and then there's no lone pairs. When there's 3 bonding groups and no lone pairs, we have what's called a trigonal planar molecule. Planar meaning they're in the same plane. Trigonal, there's 3 parts. If I was to remove one of those bonds and insert a lone pair instead, I get a bent shape. So you'll notice that the angle is still 120 for now. When we look at real molecules, the angle is going to be a little bit less than 120. We'll talk about that in a little bit. But you see, it literally is bent because the lone pair is pushing down and occupying space. The important thing about the Vesper theory is that the bonding groups count towards your geometry and the lone pairs on the central atom count towards your geometry. So just be aware of that. There are shapes based on additional lone pairs. And I'll show you a chart of those shortly. So if we go back to 3 bonding groups, we have 3 atoms bonded to the central atom. You would be tempted to think that if I added a 4th atom to the mix, that we would then take all of our angles out of 360 and divide by the 4 bonds we have, which would make 90-degree angles. However, that is not the furthest possible away all the atoms can be from each other, because we can now break into the 3rd plane, right, going in 3 dimensions. We have x and y, and now we'll break into our z plane, and we end up getting a molecule that looks like this. And this is referred to as tetrahedral geometry. All the angles, no matter how you spin it, are 109.5. And it is a fairly symmetrical molecule. All right, tetrahedral, if you think about tetra means 4, so we have 4 bonds. If you ever played the video game Tetris, all those shapes have 4 blocks. That's the way I best remember it. If you take one of those away and add a lone pair, we end up getting a shape called trigonal pyramidal. So you notice it still bends the molecule like the bent shape did, but if you look at the base, if you were to connect the atoms together and look at it in 3D space, it does form kind of a pyramid shape with a triangular base. So that's why it's referred to as trigonal pyramidal. If we add another lone pair, we get another version of the bent shape. This one has 4 domains in total. You've got 2 bonding domains, 2 lone pairs. Lone pairs are going to be referred to as the non-bonding domains. The angle is still going to be the same, about 109.5. In reality, the angle is actually going to be a little bit smaller. The simulation doesn't show angles the best when it comes to just modeling the molecules, but when we look at real molecules, lone pairs will cause our angles to get a little bit smaller. Now, what gets crazy is if when we look at things like carbon, we've previously in honors seen things that only go up to 4 bonds. When we start getting into some of those elements in that 3rd energy level that have d orbitals, we actually have the ability to form a 5th bond. It almost looks like we're combining a linear molecule with a trigonal planar molecule. You'll see that when we're looking at the trigonal planar part, it's 120 degrees around, whereas when we're looking at the linear part, the angles are 180 degrees and they're bisected by the planar part of the molecule, and we have these angles of 90 degrees. If you were to connect the dots between the atoms, you would get 2 pyramids. And so it's referred to as trigonal bipyramidal because it's two pyramids. Same deal with these. You can always add in electrons. I like this one. This one's called a seesaw because if I position it like this and move it down, it literally rocks back and forth like a seesaw. Yeah. No, that's literally why it's called that. I know. I could add another lone pair in, and I get a T-shaped molecule. So this one's pretty cool. T-shape. Literally looks like a T. Let's see, have I done 3 lone pairs yet? Probably can do 3 lone pairs. Yes. And I could have 5 domains in total and get another linear molecule. But it still has a trigonal bipyramidal electron geometry. Maybe you're seeing the pattern already, but if not, we'll explain the difference between electron and molecule geometry momentarily. We can also go up to 6 bonds. So if we have 6 bonds, angles will be 90 degrees all the way around. It's like we had a so angles will be 90 degrees all the way around, and this is referred to as octahedral. With the octahedral molecules, you can also substitute with some lone pairs. We've got square pyramidal, where we have this square base, but if we turn it upside down like this, we can form a pyramid with a square base. So we've got square pyramidal. We could add 2 lone pairs, we'll get square planar. This molecule is actually rather flat if you ignore the lone pairs. I can drag it appropriately. There you go. It's a flat molecule. Everything's 90 degrees here. And then I believe one last domain. We also get a T-shaped with octahedral this way. And last but not least, we get another linear molecule based off of how many lone pairs there are on that center atom. When we're looking at some of the real molecules, you can look at water. If you see the real bond angles, water has 2 lone pairs. We said before the bond angle for something with 2 bonds and 2 lone pairs is about 109.5. This one's a little bit smaller, 104.5. And so I would play around with this if you have a chance. Look at the real molecules and what the difference is between them and the actual angles that we are getting in our models. Okay, it is a very useful activity. Okay, so we saw that all those things move as far away as possible. When we're referring to electron geometry, the name refers to the total number of domains, so the number of electron groups. So if you're figuring out the electron geometry, you want to count up all the total bonding and non-bonding groups. If we're talking non-bonding groups, we're talking lone pairs. Whereas molecule geometry tells us the different kinds of domains. The name of the molecular geometry tells us how many lone pairs it has. It tells us if it has no lone pairs, etc. So the combination of the bonding and non-bonding domains determines our geometry and our shape. So the different types of electron groups, or domains is the other word I've used. We've got single, double, and triple bonds. We also have lone pairs. The one thing I didn't show you in that simulation is that double bonds and triple bonds still count as one bonding group. Even though you've got multiple bonds there and you start having some pi bonding there, they are still the same. They're still counting as one group to the central atom. So you'll see here we've got 2 double bonds in CO2, but it's still a linear molecule because there's 2 bonding groups. Okay, so to figure this out, draw the Lewis structure for the molecule. Then you want to determine the total number of domains around the central atom. We only care about the central atom. Determine how many of these domains are bonding groups and how many are lone pairs. The types of domains present will determine your geometry. Okay, and we have a chart for it. So we've got when we have 0 lone pairs around the central atom and 2 bonding groups, we get the linear shape. When we have no lone pairs and 4 bonding groups, we get the tetrahedral shape. When we have 1 lone pair and 3 bonding groups, we get the trigonal pyramidal shape. You might hear it referred to as angular or bent when we have two bonding and two lone pair groups. When we have one bonding group and three lone pairs, it's also referred to as linear. 6 bonding groups is octahedral. We saw square planar, that's 4 bonding and 2 lone pairs. We have a T-shape, which is 3 bonding and 2 lone pairs. The seesaw is when we have 4 bonding and 1 lone pair. And the square pyramidal is when we have 5 bonding and 1 lone pair. Okay? I'm going to post some links on I'm going to post some links on my MCPS Classroom for you to check out. It has some animations of all of the different shapes if you want to look at them more closely. Or you can play around with the simulation. Okay. So here's just another chart. I like looking at it this way too. If I count up the number of electron domains, that's what I've got here on the left side. If I count up my number of domains and find my electron pair geometry, then I can look at how many lone pairs there are to determine my molecule geometry. So this is electron geometry. All right, electron geo, and then the molecule geometry, the actual shape is over here. Okay, so I would definitely write this down. I would make some flashcards. I would even draw some pictures, memorize it however you need to memorize it. You should know all of these shapes. Okay, it will save you a load of time. All right, so just to clarify the electron domain geometry, when we talk about the electron groups, we're talking about the things involved in bonding or the lone pairs on the central atom, because those are the regions of high electron density. Remember, the valence electrons are the ones that are always involved in the bonding, and so that's why we're primarily looking at those. When we look at bonding in terms of the overlap of orbitals in the next play posit, you'll see that those other electrons are still there, and when we talk about atomic interactions, there are some repulsions between electron cloud to electron cloud with between two molecules, or two atoms, sorry. There's repulsion between two nuclei, and there's then also the attraction of nuclei of one atom to the electrons of another. Okay. So again, this just helps clarify some of the things we were looking at on the simulation. Interestingly, I don't think I put the angles on here, so that's strange. I think it's good to know the angles, or at least generally know the angles. 180, 120. For tetrahedral, 109.5, when there's a lone pair, it's typically 107.5, and when there's two lone pairs, it's typically 104.5. You may want to throw those on your index cards just to help you remember. Up to you. I think there are some questions that talk about bond angles on occasion. All right. When we get to some of the 5 and 6 domains, it gets a little bit trickier. When we have 5 and 6 domains, we got a mix of the angles. We've got 120 and 90 degrees, depending on which part of the molecule you're looking at. Here's 120, but if you're going from here to here, it's 90. So just keep that in mind when we're looking at some of the angles there, okay? When it comes to the 5 and 6 domains, the things we'll typically see that can form 5 and 6 domains are sulfur and phosphorus, because they're in the third level, right? And when you're in the third level, you've got your d orbital. This is especially popular when you see something like sulfur or phosphorus, which isn't very electronegative, being bonded to a bunch of highly electronegative groups like chlorine or fluorine or bromine. What you end up getting, we know those bonds are going to be very polar because sulfur and phosphorus aren't very polar. You're going to end up getting polar bonds that pull towards the outside of the molecule all the way around. And what that does, in effect, makes sulfur and phosphorus electron deficient due to the polarity of the bond. There's a bunch of partial positives. There's a partial positive on the center atom of your molecule, whereas there's partial negatives on the towards the outside of your atom. In effect, what this means is that your central atom's electron deficient, and then when it's electron deficient, we end up needing to form additional bonds to get the electrons we need to be stable. And here's octahedral one more time. These are 90 degrees all the way around. Okay, so here's some examples. What are the molecule geometries of the following molecules? So again, first things first, go ahead and draw them. I've pre-drawn them for you to make it a little bit easier. You want to count up the number of bonding groups. So here I count 3 bonding. I've got the number of non-bonding groups on my central atom. I've got 1 lone pair or 1 non-bonding. In total, that gives me 4 bonding groups. Or sorry, not 4 bonding groups, but 4 domains, 4 electron groups. So I know I need to look at the 4th electron domain, and then I need to find the shape with 1 lone pair. This is going to be trigonal pyramidal. Okay. Now with the second one, it's tricky because the way I drew it, you could kind of look at it and think, oh, this is linear. But remember, the central atom has 2 bonding groups. Oxygen has 2 non-bonding groups as well. When you have 2 non-bonding groups, you're actually going to have more repulsion, and you're going to not be linear. This is going to be your bent shape. So tetrahedral bent would be the proper way to refer to it. So when we're talking about electron domains and we're talking about lone pairs, I briefly mentioned it before, but lone pairs, because they take up more space and you've got 2 electrons that are already repelling each other within that region, they take up more space and they repel a little bit more than, say, a bonding group would. So when we go back to tetrahedral, we see as we add lone pairs, that angle gets a little bit smaller with each lone pair that we add. And the reason why is because the lone pairs need a little bit more space to hang around the center atom, because you've got 2 electrons that are in that region repelling each other, and they need as much space as possible. And so as a result, they then can cause repulsions on the bonding groups to happen to a more significant degree than if we just had 4 bonding groups around our atom. All right, and let's see. Go ahead and do C on your own. What is the geometry of silicon tetrafluoride? All right, you had 4 bonding groups. This one's tetrahedral. Okay, and then CO2. Do CO2 on your own. All right, remember double bonds count as 1 group. So you have 2 sets of double bonds, that's 2 bonding groups. 2 bonding groups, which means we are linear. We'll have some more examples in class if you'd like to clarify. Last thing is molecule shape and molecule polarity. Now, so we've talked about polar bonds a little bit. To be polar as a molecule, you need 2 things. You need to have polar bonds, and you need to have an asymmetrical shape. So you'll see in something like HCl, we have a polar bond, and we have 2 different atoms on opposite sides. It is definitely polar. The funny thing about this one here, we've got carbon tetrachloride. We have polar bonds, but when we look at the way those things pull on each other, they cancel out because they're pulling in equal and opposite directions at angles of 109.5. You also have the same issue going on with BF3, where they're all pulling in equal opposite directions of 120 degrees. But the minute you start substituting other groups on here, this bond's not polar, this bond's not polar, this bond's not polar. We've got one main bond that's polar, and it is significantly pulling electrons this way in our molecule. So think about that distribution. Think about the polar bonds. Think about where the dipoles are pointing. All right, and then the last thing is just this one, NH3. Whenever you have a lone pair, just assume you are going to be polar. You have a lone pair on the central atom. We know we're going to have an uneven distribution of electrons. We know that the lone pair is going to take up more space, and that there's going to be a lot of asymmetry going on. And so those dipoles, no matter how you spin it, will not cancel out. Okay? And that is all for today.